Okay. So I am still sick. My voice is still difficult today. I hope it will be okay next week. So today, we will finish the review of last semester, and we will start new material part. Okay. So last time we talked about algebra object on tensor category, and now we will consider some specific type of algebra object called separable. So an algebra object A in a tensor category C is called separable if the multiplication morphism split. So I will explain multiplication morphism M from A, so A to A split as an homomorphism of A module. Homomorphism of A module. So here we need to be careful about the meaning of split. What's the meaning of split? And we need to explain why the multiplication morphism is also an homomorphism of A module. So let me explain. Let me explain this definition. So first, first point. M is really an homomorphism of A. A module or A by module? A module. Homomorphism. Homomorphism of A by module. In fact, so why are you right that another homomorphism of A module or A by module? So wait a minute, let me check something. Okay. So yeah, it's by module. So I have a mistake in my note. So here it should be by module as an homomorphism of by module. So, which is coherent with what I said. So now we really need to check that the multiplication morphism is a homomorphism of A by module. So by the, so you see that by the associativity diagram of M. So you need to be an homomorphism of A by module. You need to be an homomorphism of right A module and of left A module. So let me mention just the right case and the left case will be the same. So that reduced to the associativity of M itself. Here you apply associativity constraint to move the parenthesis and multiplication again. So here you get where is it? Module product. Okay. So you need so this, where is that? Non, j'ai plus le truc là. Ah, voilà. This is a right. This is a right A module. Right A module. So here. This map is the module product of A tensor A as right A module. And this one, the module product of A as right A module. And this is equivalent to the associativity of M. This is precisely the associativity of M. So everything reduced to the associativity of M. So M is automatically an homomorphism of right A module. And similarly, M is automatically an homomorphism of left A module. Okay, so we have one first component. We want M to split as an homomorphism of A module. So we have that to be an homomorphism of A module. Now, what is the meaning of split? So next. M split if there is another, if there is a morphism delta from A to A tensor A, such that M composed with delta is the identity of A. In other words, pictorially, pictures. So you have A, M, from A, tensor A to A. So you represent it like that. And you have delta from A to A tensor A. So wait. Let me draw something clean. So here it's delta. And we want this to be just one line. And this to be equal to just one line, so the identity of A. So this is exactly the meaning of split. This morphism split if there exists that making the identity. So we know what is split, and now we want to split as a bimodule homomorphism. So we need also the delta to be an A bimodule homomorphism. So we have this extra assumption on delta. So finally, delta is a bimodule homomorphism. And you will see a nice diagram also for it. So what is the meaning? So it should be right, left, and right modulo A module homomorphism. So what about right? Right is this diagram. A tensor A. You apply the multiplication A. You apply delta A tensor A. Here you apply identity of A tensor M. And to be quick, you put the associativity constraint. So we want directly. We want this diagram to commute. And so this is for the right case, and you have the same for the left case. So I will not draw the diagram in details, just you have similar diagram for the left case, like that. And so what is the picture for that? The picture is more intuitive here. So you picture here. So we will call, let me write that first. We will call this assumption, the two assumptions, we called star, like that. We will mention that later as a star. And here, pictorially, this is just like that. So you start from a tensor A. You apply the delta. Here you apply the identity. And then you have identity here, and you have multiplication here. And then identity. And you have some associativity constraint in the middle. So this should be equal to the other way, like that, which is just like that. This is the right part. And the left part is similar. This is just the mirror image, in fact. On entend bien, hein? So you start from that, and then you have that. And let me write this like that. Okay. Okay, so this is the left part. So you see, yeah, so it's okay. So this separable definition can be really understood pictorially. So what I want to note here is that so this property star. So here it's just a reformulation of the fact that the splitting morphism delta is a bimodular morphism, but in fact this property, this picture, you meet these pictures for another fundamental notion for an algebra object is Frobenius algebra. So here you have this property for separable algebra, but you can also meet this property for a Frobenius algebra. We will develop later, not now, but later. But I think it's good to mention that now. So this property star for separable algebra object is shared with another fundamental notion not developed right now, soon in fact. It's of Frobenius algebra. So, more precisely, Frobenius algebra object in C. So Frobenius, what is a Frobenius algebra object? So you so it's an algebra object. Algebra object C and you have a coalgebra object. It's also a structure of coalgebra object. So we did not define notion of coalgebra object, but I guess it is the dual notion of algebra object. And here we have this delta. And it is this delta which will satisfy the above picture. So the last assumption for being a Frobenius algebra, the above two diagram denoted like that. Delta is a bimodule homomorphism. So okay. So why I talk about that? Because this is usually the picture you meet for Frobenius algebra, and in fact, because I come from subfactor theory, in subfactor theory we are very interested in Frobenius algebra because, in fact, the notion of Frobenius algebra is, in some sense, categorification of the notion of subfactor. The notion of Frobenius algebra already appears in subfactor theory. Where it is called Q system. And it's a notion due to Longo, to Roberto Longo. So in some sense, according to, so see the work of Muger, so Longo, and also of Shamindra Ghosh, the notion of Frobenius algebra is a theoretical generalization of notion of subfactor. To get a subfactor, subfactor is a notion coming from analysis, coming from Feynman algebra. So you have, you are in to deal with subfactor, you are in a very specific framework. Everything should be unitary, everything, the field should be the complex field, etc. Because the notion of Q system or the notion of Frobenius algebra object characterize the notion of subfactor for unitary fusion category. The notion of Frobenius algebra in general generalize the notion of subfactor. So in that sense, it's very, very important to me. So usually notion of subfactors M and inclusion of factor. And usually in the framework of Longo can consider factor 2-1 factor, 3-1 factor. So you don't need to care about that if you don't know factor. Funnel algebra theory. And n is given by the Frobenius algebra. Object of the tensor category of endomorphism of M. Okay. So you don't need to care about this green sentence. This is just a motivation for people who know a bit of fundamental algebra theory. Okay, so so if you take C to be just a trivial category over a field K, so there are well-known examples of separable algebra object here. So algebra, because algebra object in this trivial categories, the definition of algebra. Example of separable algebra are the one absolutely semi-simple. Absolutely semi-simple. Which means that it is semi-simple and any field extension is also semi-simple. So A is a semi-simple K algebra, and for all field extension K, this extension on A is still semi-simple. Semi-simple. So I did not prove that, but such algebra, an absolutely semi-simple algebra is separable in the sense mentioned above. Before. Okay. So now the relation between separable algebra and the category of A module. The proposition. So let A be a separable algebra object. In a fusion category. So here we need the fusion category structure. Tensor category may not be enough to prove this proposition. Then the category we define list, we review yesterday of A module is semi-simple. So the proof, we will prove that in 8 steps. So proof. So as I said, now we restart to do the proof. So, one first step. So A and A tensor A are A by module. And the first is a direct summand of the second as A by module. Direct summand means on this form. So direct summand. Okay, so this maybe this. Okay, so how to see that? You see that using the separable. So to see that you use the separable assumption. So you use delta plus the semi-simplicity. Of C, because C is a fusion category, so in particular it is semi-simple. Okay, next. So we saw yesterday that for, so we already know that for all right A M, the relative tensor product A is the unit for the relative tensor product relatively to A. Next step. So by the point 1, M tensor A, this, which is M, this is a direct summand of M relative tensor product M tensor A. And fourth step, by 2, M relative tensor product A by A is just M, and so M tensor A tensor A is M tensor A, usual tensor product, not the relative tensor product. So here you may be careful about maybe an exercise, I don't know, or be careful about something. We may need something like that. may need some associativity like that, which is so is it yeah, should we show that, or is it in the definition? We have to be careful about that. A here, because there is a quotient. So you have to be careful about that. You have to. I hope it's okay. Oh. Ça fait ça. Anyway, so next. So then you get that. So by the point, by combining all these points, so you get M is a direct summand of M tensor A, usual tensor product. Just combine 3 and 4. And so, six. So the next step. So by some lemma, by a lemma mentioned, reviewed yesterday, we have this isomorphism. So on A. M tensor A is isomorphic to C M, like that. Okay. So we define some specific A. So we saw that yesterday. And then so now C C is semi-simple. So M in C is semi-simple. Any object is semi-simple. Yeah. Particular. So by definition, C M is exact by definition of projective, exact in C. So by the above, by the previous isomorphism, this is exact also, is exact in C. And so, by definition, M tensor A is projective. Which so is projective, and any summand is projective also. So M as a summand of M tensor A is also projective in mod C A. Conclusion. any right A module M is projective. In other words, any object of mode C is projective which is equivalent to have mode C a semi-simple, because recall that an abelian category is semi-simple. So this is something well known. We already covered at the beginning of the course. If and only if every object is projective. Is projective. So this proves what you so we proved that if the algebra object A is separable. Pourquoi ça fait ça, ce truc? Oh. Ça, il marche plus, mais c'est pas grave. Anyway, there is a bug with the laser. Doesn't matter. So, if A is separable, then the category is semi-simple. And we use separable. We use separable here. Maybe I can do like that. We use separable to get that A is a direct summation of A tensor A. Okay. So, it's good time for the pause. Pause. So we'll continue after 5 minutes. Pause. Okay. So recall that. So as a C module category, semi-simple imply exact. Imply exact as for a C module category. So mode C. So mode C A is semi-simple when A is separable, so it is exact. And so by definition of what is exact for an object, A is exact. We call that the algebra object is exact by definition if mod C A is exact. Conclusion. The algebra object is separable if the algebra object is separable, then it is exact. as algebra object. And I guess of fusion category. Okay. So here is an exercise. But yeah, let me state the definition before. The definition we will see generalizing the notion of semi-simple semi-direct product in group theory. We'll get a notion generalizing that for bialgebra, and this notion will be used to characterize the category of a module of when C is just a rep, is a rep H with H a bialgebra. So let me write that quickly. So let H be a bialgebra. Let A be an algebra object. In the category of representation of H, what is called smash product. Smash product et dièse H is so the tensor product et tensor H with multiplication as follow. So A tensor, two elements multiply. So the multiplication will involve the co-multiplication of the bialgebra. So I will not write the co-multiplication with the Swidler notation, just I will write directly. So I will write something here. So with delta H sum over I H1I tensor H2I co-multiplication. So you have the usual co-multiplication, and you have the way this is a way to decompose this co-multiplication for H, and we will use that to write this new multiplication, smash product multiplication, sum over I of A so H1I acting on A prime tensor H2I multiplied by H prime. So you see here the algebra. This is the algebra structure on A, and here on H. A prime in A, H prime in H. you have this mesh product, and the exercise here is first to show that this mesh product generalizes the semi-direct product of group theory. So if H is just the trivial bialgebra coming from a group, and A smash H is just the semi-direct product, so the notion of smash product generalize the notion of semi-direct product group theory and second point of the exercise, connecting with the section, the category of A module is equivalent to the category of representation of the smash product. In general, this is for group and this is in general. So you see in this case, we can completely characterize the category of A module using a new notion called smash product. Okay. The new notion generalizing the semi-direct product. Okay. So that's all for this section. Now we will new subsection called internal. So a very useful tool called internal home in module category. Okay, so let C be a multi-tensor category. And for simplicity, we will assume it to be finite, even if what will be say in this section is also true for without assuming finite, but it will be much more easy to state in the finite case for simplicity. It will be assumed finite. So now let M be a C module category. And you consider two objects in M. Be two objects, M1 and 2, in M. So consider, so consider the following functor from C to vec X map to the home space in not on M but on M. X tensor M1 to M2. So you consider this functor. So this functor is left exact. Because the composition of left exact as a composition of Latin. Composition of left exact functor. Because there the components are left exact because C is a multitensor. In particular, the tensor functor is exact. Okay, and so it is representable. So I will explain the meaning of that. Representable. And here, in fact, the book don't prove anything, don't even refer to something. So I found a reference for that. Left exact imply representable in the finite case. So C, if you want to know, C reference by H.B. Stauffer in 71, who proved that he proved that left exact imply representable. And here, because it is finite, it can be represented by an object directly in the category. In general, if you don't assume finite, the object should be an inductive limit. But we don't go into the details here. So, what's the meaning of representable? There exists an object denoted from M1, M2 in C, and a natural isomorphism like that. Where here you put this object. So we don't need to care about the notation. This is just a notation. So there is no underlying structure. This is the notation for the object coming from the representability of this functor using this reference. And it is in C because C is finite. Otherwise, it should be an inductive limit. Okay. So we can find such object home M1, M2 directly in C by finiteness. Otherwise, we need to consider an inductive limit. This is why we choose finite, because it simplifies. Here we don't need to consider inductive limit. You can directly take an object in C. Okay, and this is what we will call the internal home definition. The object home. So this notation is, yeah, you have to be careful about this notation. This is not a home space. This is an object. So this object is called the internal home from M1 to M2. So here, M1 and M2 are objects in a C module category. But the internal home is an object in C. So be careful. Okay. Now, exercise about this home. First point, show that the functor, so the map from the opposite to C, M1, M2. This, you have to show that this is by functor. By functor. Wow. Is use the unit lemma. So the book says that by Yoneda lemma, this is a bifunctor. So I put this as an exercise. Use the Yoneda lemma to prove that this is a bifunctor. And second point, show that this bifunctor is left exact in both variables. Okay. Now, a list of natural isomorphism involving the internal home. So lemma. There are the following natural isomorphism. So the first one is the definition of internal home. So this is okay. Natural isomorphism with like that. This is definition. Next, home M1 extensor M2. Natural isomorphism with 1 extensor M1, M2. Okay. Third, internal home of between M1 and X2. Natural isomorphism. So here, when you write natural isomorphism, this really means natural isomorphism. It's a natural transformation, which is an isomorphism natural transformation between two functors. Here, we don't consider this as an object, but the functor with X mapped to that. So this is a natural isomorphism between these two functors. The functor of X mapped to that, natural isomorphism with the functor mapped to that, and as you said, natural transformation is completely characterized by a collection of isomorphism, etc. So we write directly the collection of isomorphism, but that should be understood as natural transformation. And here you can put the X outside. Internal home M1, M2, and last one. Internal home, so more or less the same, but you put X on the left. M2 isomorphic to internal home M1, M2, and you will have the X on the right with a star structure with the dual. Okay. And you will see the proof is more or less just straightforward calculation. You just need to manipulate a bit the definition. So you will see the proof is not complicated. So proof. So the first is just the definition. Okay. What about the second? So start. You start from that. M1, extensor M2. You apply the natural high junction isomorphism of C module M. So this is something we saw. So you have the natural high junction isomorphism for C module M. So you get that you can move X on the left by putting the dual. So there is a natural isomorphism still in M, so home space in M, and you put the X on the right, X dual. So we know that this works for C module M, generalizing the natural junction isomorphism on C. So this works on modulus. Next, we can apply the definition of internal home. So now we go to home space on C, extra internal home M1 and 2. So here is just the definition. And finally, you apply the natural isomorphism for C itself. And you put the X dual on the right. And you like that. So it's completely okay. Now, the third point will be very easy, but this need to use a trick coming from Yoneda lemma. By Yoneda lemma. So we want to prove that here. We want to prove that. And in fact, we can prove, so these are objects, in fact, and we can prove that on some home space. So for all of, so I will write. So this is equivalent to prove. So we are reduced to prove that for all objects in C, the home space of Y between Y, the internal home extensor M2 is a natural isomorphism with the home space like that. So what we want is the natural isomorphism. So between that and that, but we can reduce that to prove it on this home space. And why we do that? Because it's much more convenient to make some calculation. Ça c'est bizarre. Change de page. Là ça marche et là ça marche plus. le laser. Non mais c'est pas grave, c'est pas grave. Juste, tu vois, sur this page, laser work and page 6, it's they may have some specific setting. Anyway. Okay, so we are reduced to prove that. But now, this is again just a game of natural high-junction isomorphism and associativity constraint. So, reduce to prove that. Okay. C internal home M1 extensor M2. So first, this is by definition of internal home, the home on the home space on the module M. So you just write the definition of internal home here. Okay. Then you apply the natural high junction isomorphism for the module C module M. Natural adjunction isomorphism for M. And you put the X on the other side. And then you apply the associativity constraint. Just to move the parenthesis. M X star tensor Y tensor M1 M2. And then again you apply the definition of internal home. So you come back to C X star tensor Y internal home M1 M2. And finally you apply the natural adjunction isomorphism for C. And you get, you just move the X on the other side. Right. X tensor internal home 1 and 2. And so we prove what we wanted to prove. So we get, okay, so the last point, as you see, is the same as this one. So this will be proved by the same strategy. So the last point is as for 3, we are reduced to prove that for all one C, home C, Y, internal home, next, blah, blah, blah. I will write it, but natural isomorphism, home Y, internal home, M1 and 2. That's our X. Okay, and so which this can be proved exactly as for 3. So it's okay. So we proved the theorem, the lemma, sorry. And this lemma, we will apply. In fact, we will apply this natural isomorphism to prove something more consistent. Corollary. You fix an object M in a C module category. M, then you will get a C module functor. So then the functor M to C, mapping an object N to the internal home M from M to N, is a C module functor. So we get a C module functor. Okay. So proof. So as I said, the proof will use the third point of previous lemma. So recall that a C module functor require a natural isomorphism so from F n such a natural isomorphism with some commuting diagram. Removing ambiguity. So we need such a natural isomorphism. So this one is nothing but home, internal home M extensor N. This is extensor internal home M and N. And we already know that there is a natural isomorphism between these two by the lemma. So this natural isomorphism is precisely it is given by the point 3 of previous lemma. And as an exercise, check the commuting diagram. Okay. So we have a C module functor and this will be used again to prove something even more interesting, the corollary. So what is this corollary? So if M is an exact C module category, then the bifunctor, the internal home bifunctor is exact in each variable. So we already know that without assuming M to be exact, we already know that the internal home bifunctor is left exact in each variable. If you assume the C module category M to be exact, then the internal home bifunctor will be exact in each variable. And that so if M is an exact C module category bifunctor is exact in each variable. Proof. So the proof, you just need to use the previous corollary and some previous proposition involving a C module category functor. We mentioned last time. So just use the previous corollary. So we have the giving the module functor and the array and the following proposition already stated. The proposition I'm talking about is if M1 and M2 are two C module categories, and if M1 is exact, then a module functor is exact, and any additive module functor f from M1 to M2 is exact. And in fact, so then you get a corollary, and we will see next time that this can be used, such proposition can be used to completely characterize an exact module. In fact, every exact module will satisfy any module satisfying this property will be exact. So we will stop here. So let me just write that okay, no, I will. It's okay. We will mention that tomorrow. So next time we will state the converse of this proposition involving. So we can prove a converse for this proposition using the notion of internal home. So next time we will talk about, consider converse of this proposition involving internal home. By involving, I mean the proof involves internal. Okay, so we can start.